Hello, and this is the 10th lesson in this series on metric and topological spaces. This lesson is on what are called separation axioms. This video is going to be quite short. There's only a couple of definitions and some quick examples. And as always, the booklet to follow along with is in the description. So our first definition is for a T1 space. So a topological space is a T1 space if and only if, for any pair of distinct points, A and B, there are open sets OA and OB such that A is in OA and B is not in OA, and B is in OB and A is not in OB. So in other words, for any 2 points, we can find an open set containing one of the points that doesn't include the other point. And note that these two sets, OA and OB, they can overlap. They can intersect each other. They just have to not include A and B, respectively. Our second type of space is a T2 space or a Hausdorff space. And in this case, a space is T2 or Hausdorff if and only if, for any pair of distinct points, there exist open sets OA and OB such that A is in OA, B is in OB, and the sets don't intersect. So this is for any 2 points, we can surround each of them with disjoint open sets. So this is a slightly stronger condition than T1. Beforehand we said the sets could overlap, now we're saying they can't. For our first example, we've got the finite set 1, 2, 3 and the topology given there. I want to ask, is this space T1, Hausdorff, or neither? So this space is T1. So how can we show this? So firstly, let's take any 2 points, 1 and 2. In this case, it doesn't matter which 2 points we pick. For some topologies it might, but for this one it doesn't. So the set 1, 3 contains 1, but not 2. So we found us an open set containing 1, not containing 2. Similarly, we could find the set 2, 3 for the point 2. Okay, so now we've shown it's at least T1. How can we show it's Hausdorff? So we want to find, or rather, do any of the open sets containing 2, are any of them disjoint with the set 1, 3? So let's look at the 2 sets containing 2. These are 1, 2 and 2, 3. And these both intersect 1, 3. So we've seen that all the open sets containing 2 do intersect the open set containing 1. Okay, now consider R with the cofinite topology. Is this T1, Hausdorff, or neither? Have a go on your own and then come back to the video. Okay, now you've had a think. So this space is T1, and we can show that by firstly taking any 2 points. Here, let's just take 1 and 2 again. We can create the open set U1, and this is just R complement a finite number of points that includes the point 2. And this is an open set that contains the point 1, but not the point 2. And similarly, we can make a set U2 that is R complement 1 and maybe some other points. And this contains 2, but not 1. So this has shown it's T1. We still need to show it's not Hausdorff. And we can do this by saying these sets U1 and U2 do intersect. And no matter which points we pick for those ellipses, because there's only a finite number of them, then no matter what points we complement, U1 and U2 will always intersect. Okay, our next example is R with the standard topology. Is this T1, Hausdorff, or neither? Okay, have a go on your own and then come back to the video. Now you've had a go, let's go through. So this set, or this space, is Hausdorff. And we can show that by, as always, taking any 2 points. And then these sets are open balls of radius 0.4, centered around 1 and 2. Well, these open balls obviously contain 1 and 2, but they don't intersect. And we can do this with any 2 points. We can just make the balls smaller and smaller and smaller, as long as the radius of each of them is less than half the distance between the 2 points. And in fact, we can do this for any metric space. So that is, all metric spaces are Hausdorff. Okay, then finally, we have a nice theorem for Hausdorff spaces. This theorem will essentially say that the limits of sequences are unique. So you saw before that you can have a sequence that converges to more than 1 point. If the space of Hausdorff, that can't happen. So formally, we're saying that if x tau is a Hausdorff space and xn is a sequence, then if xn converges to the point x and it converges to x prime, then these points must be equal. Now the proof for this is in your booklet. So have a read through that and then we'll move on. Okay, now you've gone through the proof. Can you think of a counterexample? So that is, can you find a T1 space where the limit is not unique? Note the theorem requires us to be Hausdorff. It doesn't say T1. And as a hint, you can use the finite set 1, 2, 3. Okay, have a think and then come back to the video. Okay, now you've had a think. I'll give you at least one example. So our topology is here. The sequence is just the constant sequence 2. Well, in this space, this converges to 1, 2, and 3. So here, the limit is not unique, and that's because our topology only gives us a T1 space, not a Hausdorff space.